In this video, we're going to cover topic 5 of statics, and that is equilibrium of a rigid body. We're going to learn how to develop equilibrium equations for a rigid body, so we're going to extend what we did for particle equilibrium now to a rigid body. We're going to introduce a really important concept called free body diagrams, which we're going to abbreviate as FBDs. We'll be using FBDs pretty much for this topic and the remainder of statics. And then we're going to be able to solve for rigid body equilibrium problems by drawing an FBD and then solving the equations of equilibrium that we develop. So before we jump into some examples, let's kind of go over what rigid body equilibrium entails. So I have this kind of arbitrary shape defined here for you. And this shape is subjected to a few forces and moments. And we have some point O, which is some arbitrary point on the system. It can be on or off of the system. It's just a point basically where we're going to take the summation of our moments and forces at. So we can take this system here that has 4 forces and 2 moments acting upon it, and we can reduce all of these forces to one resultant force and all of these moments to one resultant moment. And we know that the summation of all of these has to be equal to 0 because the system is in static equilibrium. Okay, and that's the equilibrium equations that we get. One thing that we're going to assume in this class, whenever we're applying the equations of equilibrium, is that a rigid body remains rigid. Now, in reality, there's no perfect system where really when you apply a force, there's no deformation at all. But that's an assumption that we're going to make, and we're going to apply this to types of materials and systems where the relative deformation is very small. So we're able to make this assumption and use it for engineering applications, especially in this class. Okay, we're going to start by covering equilibrium in one dimension. We're going to stick to coplanar systems not one dimension, in 2 dimensions, 2D. That's a coplanar system, which means we're dealing with the XY coordinate plane. Whenever we're talking about a couple or a moment, which is basically a rotation, if it's in the 2D plane, that means the rotations act along the z-axis or the third axis, which is not defined. So we're still dealing with bending. Okay, we're not going to be dealing with any torque or twisting for this topic, but we're still dealing with bending that occurs along basically perpendicular to that z-axis. I have a picture here for you of a plane, which we are calling a rigid body. And this is a really simplified form of a free body diagram. So we have the weight due to gravity of the rigid body acting down at the center of gravity here, or center of mass of the system. And we have the force, the normal force that the 2 tires make in the front and the 1 tire makes in the back. Okay, this is kind of just a really simplified FBD or free body diagram. Which basically shows all of the forces acting on the system. We're going to be going over those in more detail in the next few slides. This is one of the most important objectives that we're going to learn in statics, because drawing a free body diagram, or as I'm going to refer to it for the rest of this topic, an FBD, is the first step in getting your answer right. You can't really set up your equilibrium equations correctly if you have the wrong FBD, okay? Everything that we're going to draw, it matters which direction we are assuming and then which direction we figure out is the correct direction of our forces and our moments. So this is a really important step. So take some time to kind of draw out the problem before you just jump into solving it with the math. An FBD by definition is a diagram that accounts for all unknown and known external forces and moment. And I've bolded and highlighted external because you're not including anything that's happening internally in the system. So remember, if you go back to our support page, an internal reaction would be like an example, a hinge. Therefore, don't add hinge forces on an FBD unless you break the system up. And I'll kind of show you what that means in the following slides as well. Okay. Support reactions have to be included in FBDs. So you might be wondering, what is a support reaction? And we're going to kind of go over that before we get into drawing FBDs. So the first question here is, what is a support? A support is something that you need to support your structural system. And your structural system is what's taking the loads. So let's say you have a beam that you're designing, or let's say this is a bridge. Okay. Your bridge has loads on it, right? These are cars driving by, or trucks. That equals load. Okay. Now, your bridge doesn't just hang in thin air, right? It's being supported by something. So whatever it's being supported by, okay, we call these supports. That is a really strange way of spelling supports. Okay. And we have some commonly used supports that we're going to go over, but each support, if the bridge has some load due to these trucks, the support imparts a load back. And then this support imparts a load back. So for example, if these loads are 10 kips, 10 kips, 10 kips, that's 30 kips. If this was all symmetric, I would have 30 divided by 2 on each side pushing back to support that bridge. Okay. A support is basically now any object that prevents translation or rotation in a specified direction by exerting a force back on the body in the opposite direction to stop the movement. That's the formal definition. So let's go back to this bridge example that I have for you. I told you that I have 30 kips of loading on top of the bridge. The support needs to come back like the normal force and give an equal and opposite reaction. So we have two supports to give an equal and opposite reaction. The supports have to add up to the loading applied. So applied loading (30 kips), support reactions are 30 kips. And this has to happen to be in static equilibrium. Okay, I have some real life examples of supports here for you. This is a hinge. And you can see that is also, the hinge is basically what we use to open and close our doors. I've gone over this example a few times in my previous videos in the class. This is like the easiest way to kind of visualize what a hinge does. A hinge on a door frame basically allows you to open and close the door through what kind of movement? Rotation. However, you can't translate up and down on the y-axis or left to right on the x-axis. If you wanted to move a door up and down, you have to break it off of the hinge to do so. So the hinge does not allow translation. No translation, only rotation. That's an example of a support. Okay. I have a few other examples here for you. Let's take a look at this one. These are steel beams framing into a concrete wall, and they're fixed, which means they're bolted basically. This is a fixed connection. They can't move up and down, they can't move left to right, and they can't rotate unless you were going to break the system. Okay. Here's an example of an experimental setup with a beam. The beam is supported by rollers. Okay. You see these two circular objects, and what a roller what a roller does is it provides vertical support, so you can't translate up and down, but you're allowed to translate side to side, and you're allowed to rotate. So a roller only prevents movement perpendicular to the surface it's on. It just basically provides a normal force. Okay. Here are some common types of supports and reactions, simplified, and I'm going to go over a table with you that I'm going to be referring back to in almost like every topic from here on out. Okay, and we'll show you all of those support reactions. So here I have kind of broken down what I went over in the previous slide, but we have the fixed support, pin support, and roller support. These are the three most common supports that we use in engineering, okay? The fixed support in the real world looks like this. When we draw in engineering, we always draw it with a straight line that kind of looks like it's fixed to a surface like this. A fixed support does not allow any rotation or any translation up and down or any translation left and right. It's fixed, meaning it cannot move at all. A pin support kind of looks like this triangle shape, and when we're drawing it for problems, we always draw it like this. You can kind of see this like triangle, okay? A pin allows for rotation, so you can rotate side to side, but there's no movement up and down or left and right, so no translation. Okay. The pin is the same thing as a hinge, so let's talk about this. Pin is the same thing as a hinge for the most part. The difference is a pin is external, so it acts at the ends of the member, while a hinge is internal. It acts in the middle of the system. They both do not prevent rotation. They allow rotation to happen. But they do prevent translation in X and Y. Okay. Now, this is the table I was telling you on slide 10 that I'm going to be kind of referring back to. I'm going to go ahead and highlight the really important support reactions that we'll be going over a lot. The roller, the pin and hinge, the fixed support, and the second kind of important ones are also rockers, which is the same as the roller. If you see a rocker, that's the same as a roller. Okay. Try to see which other ones we'll be using a few times. These ones are pretty straightforward. The cables, it's like a cable has a tension force coming out. But really, for the most part, it's going to be 3, 8, and 10. Okay. Now, in order to draw our FBDs, we need to understand what internal forces are, even though our FBDs are only going to include external forces. Okay. So internal forces are forces that act inside of a rigid body instead of externally, like applied loads and reaction forces. Okay. If we remember Newton's third law, it means that we have equal and opposite reactionary forces. So whenever we see equal and opposite, that means equal in magnitude, but opposite in direction. So for every action, there is an equal and opposite reaction. If I place my hand on a table, that table exerts an equal and opposite normal force coming right back up, and we learned that from physics. Okay? Because these internal forces cancel each other out, like my hand on the door and the door pushing back on me, I don't need to include internal forces in my FBD. Okay? Later on, when you get to mechanics of materials, these internal forces will become really important because they're going to lead to basically calculating the stress of a system. Right now, we're not dealing with stresses because this class we're trying to figure out everything that's happening externally in the structural system. Once we get to the point where we're discussing stresses, then you can worry about internal forces. But for now, we're going to focus on external forces. One of the most commonly used external forces is weight due to gravity. And so we're going to have to know how to calculate the weight, which is mg, and also where the center of gravity of an object is. So when a body is within its gravitational field, every single particle that constructs that body has some weight associated to it. what we're going to do as engineers, because we're going to simplify these problems, we can reduce the weight of each and every particle acting in the system to a single resultant force acting at a specific point, and that specific point is going to be the center of gravity. Okay? If the body is uniform, which means it's all made from the same material, then the center of gravity is the same as the geometric centroid. Okay, so for these problems, we're going to be dealing with particles or bodies that have uniform material. If it's non-uniform, then the location of the center of gravity has to be given. We're not going to be calculating that on our own. The next thing I want to talk about before we jump into a problem is an idealized model. In engineering, we have to take real examples and we have to build analytical models from those examples. So we sometimes simplify those models in order to make our lives easier and make the problems that we're solving a little bit more simple. So what we do is we take kind of complex real-world models, like complex trusses or bridges, and we simplify them into something that's really easy to solve for. Okay? Here are some examples, or here's one example of an idealized model. So here we have a steel beam spanning from point A to point B. Okay? Along these steel beams, we have roof joists. So these roof joists here, try to highlight them, are placed on top of the steel beams. So one thing we do to get from this actual real-world model to the idealized model that looks like this is we can say that those roof joists actually just impart some point load on the beam. Like this, some force F. These are all from those roof. Okay. Now, we make a few other assumptions here in order to go from this idealized model to the analytical model. So this is called the analytical model. Okay. We're also going to assume that on one side we have a pin and on one side we have a roller, because for the most part we are not allowed to move in X or Y, allowed to rotate. And for a roller, not allowed to move in Y, allowed to move in X, rotate. Okay? In our problems, I will give you these support conditions. You don't have to come up with them yourself, and I'll explicitly tell you what they are. So I'll say this is a fixed support, this is a roller, this is a pin, but you would have to go to this table or eventually kind of be really quick in knowing what reactions occur due to what types of supports. Okay, so let's go ahead and let's try example 1, where we're going to build an FBD. So let's draw the free body diagram. I'm going to draw this model here. Fixed support. And I would tell you again that this is fixed if this was an exam problem. Point A. I need to draw all of the external loading. So here I have 1200 newtons. That's pretty much all I have acting on the beam. And now I need to draw the reactions for a fixed support. So I'm going to go to table 10. I'm going to find where it says fixed support, and you can see I have 3 reactions for a fixed support. I have Fx, Fy, and M, and I'm going to go ahead and draw those on my system. I'm going to call them Ay, Ax, and moment at point A. Okay. Now, I also need to put the weight due to gravity on the beam. So here in the middle, at the center point, because this is uniform, which means same material, same area, I have 100 kilograms, so 100 times acceleration due to gravity, because weight is mg. Okay. Okay, let's move on now, and let's continue and go over example 2. So example 2, I have a diagram of a foot lever, and it's shown here that the operator of the lever applies a vertical force to the pedal. So this is the pedal, and this is the person's foot on the pedal. Okay. There's also a spring that's basically stretched by 1.5 inches as the force is applied at point B, and we have 20 pounds of force there. Okay. So this real world model, I'm going to kind of highlight it here. Okay. And this force can be idealized as this system here. And what we want to do is we want to draw the FBD here. So we've already got the force F applied from the person's foot, right? And the next thing is we want to draw the force that goes through this link at B, which we were told is 20 pounds. We also have this force of the spring, which I'm going to call Fs. And we're given K, so Fs is equal to K times S, which is the stretch of the spring. So we have 20 pounds per inch times the stretch of the spring, which is 1.5 inches. So we get a force of 30 pounds. Okay. Lastly, we have a pin at point A. So if we go to table on page 10, and we look for the pin, we see that the pin has an Fy and an Fx. So we're going to come to our FBD, and we're going to draw an AX and an AY. And this is our FBD. When I start going through some examples with equilibrium, you'll kind of see that it doesn't matter which direction you choose, whether going in this direction or this direction for AX, or this direction or this direction for AY, because the problem will kind of tell us as we solve for it which direction is the correct direction. Okay? All right. So our equilibrium equations are the exact same equilibrium equations that we have for a particle. We're just adding in the moment function now for equilibrium because this is a rigid body. So we have summation of forces in the x is 0, y is 0, and summation of forces of our moment is also 0. Let's go ahead and apply this to an example and see how this procedure is done. So we want to determine the horizontal and vertical components of the reaction on the beam caused by the pin at B and the rocker at A. Neglect the weight of the beam. So this time we don't need to add the weight due to gravity because it's telling us to kind of let it go. I'm going to redraw this system here. It says we have a pin at B and a rocker at A. The rocker and the roller are the same thing. I have 200 newtons here, 100 newtons here, $600 newtons here, okay. Now, what else? I have that the thickness of the member is 0.2. And I think I have everything on here now. Now all I need to do is go to page 10 and add in the support here for a rocker, which is a support perpendicular to the surface. So I'm going to call this AY. And then for the pin, I have two support reactions. and a BY. Okay. The BX is, I'm going to kind of move it. It acts in that center point. Okay. Now what I'm going to do, this is my FBD. This is the diagram that you need to draw before you can solve for equilibrium. So FBD is 1. This is always step 1. Now step 2 here is to solve for the reactions using our equations. Using our equations of equilibrium. Okay. So I'm going to put the 600-pound force into reactions first. So if I bring it down along the line of action to this point here, and I want to split it up into the x and y components here, I end up getting, for my x component, 600 cosine 45. I was given 45 degrees here. And 600 sine 45. Okay. Now I can go ahead and easily put everything into my equilibrium equation. So let's start with summation of forces in the x direction and set everything equal to 0. I'm going to say that going to the right is positive. Everything in the x direction would be the 600 cosine 45 minus bx equals 0. I end up getting bx is equal to 424 newtons. I'm going to go ahead and sum moments about the pin now. Counterclockwise is positive. I'm going to start with the 100 Newton force because it's the closest one to me. 100 newtons times a moment arm of 2 meters plus 600 sine 45 times a moment arm of 5 meters. And I also need to add in the 600 cosine 45 because if you see, 600 cosine 45 goes around point B and it has this little tiny moment arm equal to the thickness of the member. So I also need to subtract. And then lastly, minus AY. And I can solve for AY as 319 newtons. And then my last equation here, summation of forces in the y equals 0, up is positive. I get the 319 from AY minus 600 sine 45 minus 100 minus 200 plus by equals 0, and I get by equals 405 newtons. Okay, let's go ahead and try example 4 now. We have a cord and it supports a force of 100 pounds and wraps over a frictionless pulley. Determine the tension in the cord at C and the horizontal and vertical components of the reaction at pin A. So I'm going to redraw this here. If I want to start by drawing the FBD here, basically if I have a pin at point A, I have an AX component, this is again from table 10, on page 10, and an AY component. I also have some tension T in the cable here, and then I have 100 pounds being pulled down here, and that tension acts at an angle of 30 degrees. Okay, this is actually my FBD that I just drew. Now if I want to apply equations of equilibrium here, I can start by summing moment at point A, setting it equal to 0, saying counterclockwise is positive. I end up getting the 100-pound force times a moment arm of 0.5. And then the T here, if I draw a line through the line of action of T, you can see that it always acts 0.5 feet away. So, and it's rotating around point A clockwise. So I'm going to get minus T times a moment arm of 0.5 equals 0. So T is basically the 100-pound tension in the cable. I'm going to also sum forces in the x direction. Right is positive. I get negative AX plus 100 sine 30. AX equals 50 pounds. The 100 sine 30 is the x component of force T. Okay. And then lastly, I have the summation of Fy equals 0. Up is positive, and I get AY minus 100 sine 30 equals 0, and AY equals 187 pounds. All right, let's try another example here. We want to determine the horizontal and vertical components of the reaction on the member at the pin A and the normal reaction of the roller at B. Okay, so of course, our first step is the FBD. I'm actually just going to draw it directly on here. So if I have a pin at point A, that means I have an AX and I have an AY. I have the normal reaction to the surface, right? It's perpendicular to the surface. I'm going to call that B, normal. And then I have the 750-pound load and everything else I already know. Okay. If 30-degree angle acts there, that means, okay, I want to make sure, let me draw this so it's a little more clear. The normal reaction at B. Okay, you can easily kind of go through the geometry of this here and see that if this is 30 degrees, that means this is 60 degrees, which means this is also 30 degrees. Okay. This will help you split BN up into those components there. Okay. So basically, when I pull BN up, I'm going to have B sub N cosine 30, B sub N sine 30. Okay. I think we're ready now to do equilibrium equation. So 1 FBD, 2 equilibrium. Let's sum the moment about point A, set everything equal to 0, counterclockwise is positive. We have the NB cosine 30 times 6 feet minus NB sine 30 times 2 feet minus the 750 times a moment arm of 3 feet. And we get NB is 536.2 pounds. One done. Let's go ahead and continue with summation of forces in the x0. Right is positive. we have AX minus, I'm going to plug in NB 536.2 sine 30. We get AX is 268 pounds, and we can now solve for FY forces. We have AY plus 536.2 cosine 30 minus 750, and we get AY is 286 pounds. Okay. Let's move on. Try example 6. Again, determine the support reactions on the member. There's a collar at A fixed to the member, and it can slide vertically along the vertical shaft. So this is one that I hadn't highlighted, but is still important to know. So from page 10, this is the member fixed to a collar. Basically, it prevents translation in one direction and prevents rotation. So those are the two reactions that we're going to include. Let's start with our FBD. It can slide vertically, which means it cannot move in this direction, so we have to put a reaction to stop the movement. We also can't rotate, so we have to put a reaction to stop the rotation. At B, we just have a roller, so just a BY. And everything else is already there, so that's all we have to put for our FBD. Now let's go ahead, this is step 1. I only have one force in the x direction, AX, so it's equal to 0. Nothing else to put there. And then lastly, I have my summation of moments. I'm going to sum my moments about point A. Counterclockwise is positive. And I need to add in, of course, the summation of that moment. And then I need to add in the 900 times the 3 plus 1 cosine 45. And let me show you how I got that moment arm. So if I'm summing moments about point A, right there, and this is BY, it's 900. I'm going to draw a line through the line of action of the force, and then I'm going to draw a line perpendicular through point A. That means I need this distance. I know from here to here is 3 meters, but from here to here, this little portion, I need to get from the triangle. So if the hypotenuse of the triangle is 1, and this is 45, that means that this part is 1 cosine 45. So the moment arm is 1.5 meters plus 1.5 meters plus 1 cosine 45, which comes out to 3 plus 1 cosine 45. Okay, if I solve for this, I end up getting MA is 1.49 kilonewton meters clockwise. Okay, let's move on. Let's go over some extra tips and tricks for solving problems. So, one extra tip that we can talk about is something called a two-force member. A two-force member is a member that has forces only applied at 2 points on the member, exactly how it sounds, a two-force member. Okay, so here are some examples. If I have a member here, this curved member, and I have points A and B, and I have a force FA and a force FB, I know to satisfy the equilibrium, FA has to be equal to FB. So I'm going to call them both F. And if that's the case, the moment equilibrium also requires that FA and FB share the same line of action. Okay, they must be directed along the same line, and that line joins points A and B. So draw a line of action through A and B. Okay, and basically, to be classified as a two-force member, we have these two requirements. One, they have to be equal in magnitude and opposite in direction, and they have to lie on the same line of action, directed along the line joining the 2 points. Okay, if these hold true, then the member is a two-force member. Okay, here's an example of a two-force member. It's a hydraulic cylinder from point A to point B. This is a pin connected at the ends, and only pin forces act on the member. So the resultant of those pins ends up going through the member. So we only have those two forces, basically. So this is a two-force member. We also have three-force members, which basically means we have forces that are applied only at 3 points on the member. Moment equilibrium can be satisfied only if the three forces form a concurrent or parallel force system. A concurrent force system means all the lines of action of the force go through 1 point. So let's see how that works. This is concurrent. Here's a line of action of F1, line of action of F2, line of action of F3. They all go through point A, so those are three force members. The next option is that all the forces are parallel. So you see F1 is parallel to F2, parallel to F3. This is also considered a three-force member. An example of a three-force member here is the boom and bucket on the lift, basically. The line of action of the weight and the force of the two members at B, FB, intersect all at point O. So let's see how that looks. This is the weight. FA, FB, all intersect around a common point. Let's go ahead and do an example here of a two-force member application. The levers shown supported at A and connected to a short link BD. If the weight of the member is negligible, determine the force of the pin on the lever A. Okay, so here we can see that BD is actually considered a two-force member. Let's see why. Okay. Basically, the resultant force from the pin, D and B, okay, must be equal and opposite and collinear. Okay. So what we see here, if we isolate that link, we don't have any other forces applied. We have the resultant of that pin, and then we have the force that it exerts opposite. Okay. The magnitude of F is unknown, but we do know the line of action passes through F. So, don't know. It passes through line BD. Okay. Along with that, we also have a three-force member, which is ABC. Okay. Basically, to satisfy moment equilibrium, if ABC is a three-force member, then 3 non-parallel forces acting on it must be concurrent at point O. Okay? So, F acting on lever B, basically, is opposite to F acting at B on the link. Let's go ahead and let's solve for this system. So here, I have an angle of 45 degrees. Actually, this is drawn for us here really nicely, better than I can draw it. So here to get theta, which is the angle that the 3-force member ABC makes with the horizontal, I can say theta is equal to inverse tangent of 0.7 over 0.4, and I get 60.3 degrees. Now I can sum forces in the x direction here. I would get my FA right here, cosine 60.3 minus F cosine 45 plus 400 equals 0. And I can sum Fy equals 0, up is positive, and I can now solve 2 equations and 2 unknowns for F and Fa, and I get 1.07 and 1.32. Okay, you can also solve this by representing the force at A by the 2 components like you would normally do. So you can absolutely solve this without recognizing that we have the 2 and 3 force member. It would just be a little bit more complicated. So it's absolutely possible, instead of solving for theta as an unknown, you would just have gone directly and solved for AX and AY, and then you could have solved for F and theta if you need to. Okay, this is just a simple trick that makes it a little easier to solve for. We're going to now go over some extra equilibrium examples in 2D. Okay, let's start with example 8. So we want to determine the reaction at the support tier, and we have a distributed load. So let's start by drawing the FBD. At A we have the roller, so we have an A normal. At B we have a pin, we have a BX, a BY, and then we have a triangular distributed load. So the resultant acts at the center of that system because it's symmetric, and the value is the area of the triangle, so 100 times 400 times 6. That is our FBD. Next step is equilibrium. To solve for the unknowns, I'm going to sum moments at point B to start with, counterclockwise is positive. 1/2 times 400 times 6, moment arm of 3, minus A normal, the 4/5 component times moment arm of 6 equals 0. I end up getting AR equals 750 newtons. Now I'm going to actually go ahead and solve for a moment about point A now to show you that you can also use 2 moment equations and 1 force equation if you like, as long as you only use 3 equations. If you try to use multiple moment equations and you use like 4 equations, you'll just end up getting a redundant answer and you won't actually solve for more unknowns. And then a moment arm of 3, and we get By is 600 newtons. And then to solve for our last Bx, we can sum forces in the x direction, and we get the 750 AN, which is the 3/5 component, minus Bx equals 0. and we get Bx is equal to 450 newtons.